Let us try another example. Again, we are dealing with the same column. The specifications are still the same, except that the conditions for the columns is different. We are now dealing with the unbraced column, which is slender. The loading will be the same, only that the moment is acting in the minor axis of the column. That gives you the slender column, unbraced structure, uniaxial load, which is acting in the minor axis of the column. The purpose of this example is to demonstrate different calculations of the column under different conditions for you to observe the standard design process of a column. The example is purposely designed for the same column so that when you observe the calculation steps from these examples as well as the previous examples, you are easier to detect the differences in terms of the calculations under different circumstances of the column. Since we have discussed quite extensively regarding the design process of the column over the last few examples, our focus now it will be highlighting the unique calculations part for the column, whereas the common part, if you wish to know more, you may refer to the previous videos. Without further ado, let us get started. Now this column is unbraced, slender, and you have uniaxial load where the moment acting in the minor axis. Again, we will start with calculating the concrete cover. The reinforcement bar size 16 mm. That means C means bar it will be 16 mm. Exposure class XC3. That means C mean durability it will be 25. Your concrete cover ultimately it will be equals to 35 mm. The structure is an unbraced structure, and you know that it is a slender column. Slender column, unbraced structure. You should sketch this, where your MED it will be based on these equations. There are first order moment and second order moment. Superimpose both, you get the final moment. This design moment here needs to be at least greater than the M mean. Same process will deal with the first order moment. Nothing new, you need to get the moment acting onto the column, which are 13.3 and 7.5, to be added up with the moment due to the imperfection, which is calculated by having the axial loops multiplied with the EI. EI is calculated on basis of the effective length divided by 400. The effective length is given 4.348 meter, which is the extensions from the slenderness check for the unbraced structure. We are talking about the minor axis, 4.348 meter. The slenderness ratio in the minor axis it will be 104. Use the effective length 4.348 divided by 400. You get your EI equals to 10.9 mm. Multiply the EI with the NED, which is 49.12 kilonewton. You get moment due to the imperfections plus the moment acting onto the column. Two moments acting onto the column. The bigger value will be the M02, while the smaller value will be the M01. If you refer to the equations for the unbraced slender column, you don't have to calculate the NOE. Even though you don't calculate this, also never mind. At the end of the day, it shall not govern your MED. Once you're done with the first order moment, you need to deal with the second order moment. To get the second order moment, you need the E2. There is a series of equations to determine E2. Most of the equations you have the value except for the Kr, which at the moment you don't know the amount of reinforcement. Not knowing the amount of reinforcement, you can't get the Kr. So in this case, we shall first assume the Kr, and then later we work out the curvature 1 per r, subsequently E2 and the M2, until we get the MED. Use the MED calculated in the design chart for you to get the AS. Only then you get the AS. Substitute back into the equations for you to get the Kr, and then check the Kr. If the Kr is the same as what is assumed, then no change to the M2. When M2 does not change, that means your MED will be converted. In the case that the Kr is not the same as what is assumed, that means there will be revisions in terms of the M2, which ultimately will change the MED. Then you will use the new MED and find the AS from the design chart. You will repeat the process until you reach to the state that the Kr here is consistent. Then you can confirm the M2 and subsequently convert the MED. Then whatever AS that calculated, that will be the finalized AS. The calculation process is demonstrated here. Assume the Kr equals to 1.0. The rest of the equations, it will be similar calculations as per what we have discussed previously in our previous example. If you wish to know more, you can refer to the previous videos. You have the equation here to demonstrate to you how those values are obtained. Having the 1 per r0 and the K5 as well as the Kr, you assume the curvature 1 per r. Substitute this into the equations to get E2. The C is a constant, 10, and the effective length here is given 4 point something meter. Now you have your E2 equals to 90.5. Substitute the E2s into the equations, multiply with the NED, which is 49.12. You get M2 equals to 4.4 kilonewton meter, referring to the equations for the NED for the slender and unbraced column. M02 we have calculated earlier on, which is equals to 13.8. M2 is calculated as 4.4 with the assumption that the Kr equals to 1.0, and then the value calculated after the summations shall be greater than the Eng-aim. Eng-aim is calculated by multiplying the NED with the E0. E0 shall be equals to H divided by 30. The H here refers to the dimensions of the column. Since we are dealing with the minor axis, the H shall be taken as 150. The calculated value here shall be at least 20. That gives you E0 equals to 20. Multiply the NED, you get the Eng-aim equals to 0.98 kilonewton meter. You will choose the larger value of the two. Obviously, the MED it will be due to N02, which is 13.8 plus 4.4. You have NED equals to 18.2 kilonewton meter. Having the MED acquired, your next step it will be to get the y-axis and the x-axis for you to find the AS from the column design chart. First, you need to decide on the column design chart to be used. Calculate D2. D2 is referring to the edge of the column to the center of the reinforcement, which is the concrete cover 35 plus the size of the shear link 6 mm and plus half size of the reinforcement bar, 16 mm. That gives you 49 mm. Get the D2 per H ratio. The H here, since that we are dealing with the minor axis, that means we are talking about this 150. We have D2 per H ratio of 0.327. Therefore, we search for the suitable chart. For the chart available, the largest D2 per H ratio is 0.25. We don't have any chart beyond that. Therefore, the chart of 0.25 is used. Although you are using the chart of 0.25, where else your actual D2 per H ratio is actually greater than that, we have discussed in our previous videos. The calculated AS here will be safe. The smaller D2 per H ratio will give you more conservative design. With that, let us just use the chart 0.25. Get these two values, one for the y-axis, another one for the x-axis. NED 49.12, B and H 150 times 300, FCK 30, you get 0.036. As for the x-axis, the M here refers to the MED. We have calculated the MED equals to 18.2 kN divided by BH square FCK. Bending in the minor axis, that means this will be the B and this will be the H. BH square times SCK, which is 30. You get the x-axis equals to 0.09. Refers to the chart 0.036 and 0.09, which is somewhere here. Let's say we get the numbers equals to 0.3, which fall at the line of 0.3 here. The AS required, it would be 810 mm square. This shall be the AS that you use to calculate the KR. To check if the assumed KR is the same as the calculated, substitute the AS at 10 mm square into the equations for the omega. Multiply FYD, which is calculated from these equations, 435, divided by AC, 150 times 300, and also divided by FCD. From these equations, your FCD is equals to 17. Get the omega, substitute into the equations, get the NU. Calculate the N, NED divided by area of the column divided by FCD. Substitute the relevant value with N balance assumed to be 0.4. The calculated value here should not be greater than 1.0. The calculated KR here is more than 1.0. Then we limit it to 1.0. Now this 1.0 KR is the same as what we have assumed earlier on. That means no change to the KR. Then the rest of the calculations to get the M2 will still be the same. Having the M2 to be the same, that means the MED will be the same. And then the amount of reinforcement bar area required, it will be 810 mm square. You're going to provide the reinforcement bars to be greater than this. Let us try with 4 units of 16 mm rebar. The total rebar area is only 804, which is less than 810. That means it is insufficient. You will need to adding another 2 reinforcement bar of 12 mm diameter, giving you this amount of reinforcement. That gives you 4H16 plus 2H12. In terms of the rebar arrangement, this will be your column. 4H16 plus 2H12. you will need to be extra careful with the arrangement of the reinforcement. The 2H12 should be here, but not here. Why is it so? Because you need to use those rebar to take the moment. If you put that 2H12 here, that means these two reinforcement bar contribute nothing to the rotations in the minor axis. In this case, even though you add up 2H12, as far as the minor axis is concerned, that 2H12 is not functional, which will lead to you failure of the column. Your provided AS is insufficient without this 2H12. This brings us to an important understanding. The arrangement of the reinforcement, you must always cross-check with the directions of the moment. Make sure those reinforcements is actually contributing in resisting the moment. You can't simply put there. Next question. What if you choose to have 4H16 plus 1H12 and your total AS here is sufficient? Normally we won't do this. This is because of the symmetrical issue. Imagine this is your column 4H16 plus 1H12. It is not symmetrical. Therefore, a better solution is for you to have 2H12 in addition, and it is supposed to be placed in the manner that contributing to the moment resistance. Having the amount of reinforcement bar confirmed, you will check the AS mean. This process is typical. Simply substitute the equations, you get those values, and then check for the AS max. Based on the amount of reinforcement bar provided, divided with the cross-sectional area, 150 times 300, your provided reinforcement bar constitute about 2.3% of the total cross-sectional area. It is less than 4%, that means it is acceptable. At the lapping regions, the amount of reinforcement bar shall double, and it is less than 8%, that means it is acceptable. And then we'll proceed with the requirements for the link. This one is also typical. We have discussed about this in our previous example. With that, ultimately we get the 6H150 throughout the column, and then at the joint as well as at the lap region, you will use 6H75.